Okay. All right. So we are talking about electric flux, and we were talking about how can we calculate electric flux through any surfaces. Yeah. And the concepts of flux is just like the way that you can sort of like quantify the amount of electric field lines that penetrating through any particular surface. That's it. That's the whole thing. So we sort of like we define the way that we can calculate the number of flux. Okay. So what we can summarize in a very short equation, it looks like this. Flux is just the electric field vector dot with the area vector. And everyone's agreed with me last time that the way that we can create the area vector is just by just having a regular piece of area, and then you just draw a vector perpendicular to that piece of area. Okay, so that is going to be the directions of that area. Cool. All right. So just like a quick reminder. So this one is just the area surface. The width times the height, or the length times the width. And then you give it the direction normal to the actual surface. Okay. So that's pretty cool. So what you have today is now we're going to really do the calculation. So we're going to start off from something very simple. It's just a cube. All right. And hopefully by seeing this example, you will see how eventually we are going to be able to calculate flux on other kind of surfaces. So consider a uniform electric field E oriented in the X direction. So as you can see, there's that electric field lines pointing along the positive X direction there. Find the net electric flux through the surface of a cube having the edge length L. Cool. Oriented as shown in the figure. All right. Can you sort of like guess what would be the net electric flux here?
Okay.
Just guess. Like we haven't, I mean, we are not doing any calculation just yet, but can you just give like a guess like, hey, at the end, I should get something. What is that something? What do you think? All right. So imagine from last time we were talking about what does it mean by flux, right? It can be positive, it could be negative, it could be zero. So whenever the flux, the electric field lines, it's trying to enter a closed surface. So it means the closed surface will enclose a volume. You guys with me? So if you look at this particular example over here, a cube that you are seeing here is a closed surface. It's wrapped around itself. So that means there is an internal volume inside this cube. Make sense? Okay?
Okay.
And then look at this. Electric field is actually trying to enter this volume from the back side on the left. Can you see that? So let me highlight that portion over there. So if you can see, if I'm highlighting this area here, let me call this left side area. So you can see the electric field is trying to enter the box. Think of it like this is like a box. So electric field is actually penetrating inward from that side. And then if you look at the right side surface that I'm sort of like highlighting in blue over here, you can see that electric field is actually coming out. So it's exiting the box on the right side. But when you look at this electric field line, well, Ajahn, electric field has the uniform pattern, and the magnitude of electric fields is just a constant. So that means the number of lines that enter the box must be the same as the one that is going out from the box. Does that make sense? So at least what you can think of this one at the end, you can expect that the net, let me call it like a sum of the flux on all surfaces should be zero. You think so? Agree?
Okay.
All right. So let's do the calculation, shall we? So we understand more about how to calculate flux. So what I'm going to do is this. The net flux that you are going to get is going to be flux that's going through the left side. So let me call flux L. That's on the green surface there. And then there will be flux on the right side that I highlighted blue. And then, of course, there will be all the flux, all the surfaces that comprises the side of the box. So there'll be the top. This is the top surface, the front, the bottom, and the back behind that one. Yeah, there's a back there. But you guys can see that, okay, let me call this the flux on the side. Yeah, the top, the bottom, the front, and the back. Those four surfaces won't have any electric field penetrating through whatsoever. You guys with me?
Okay.
Yes, yes. All right. So you can conclude right away that the flux going through the top, the bottom, the front, the back, there's none. There's nothing there. Okay. So you only need to take into account the flux on the left and on the right surfaces. Cool. All right. So let me take a look at the left side surface first. So you guys know right away that the area of this one, so let me highlight this one here. The area of this is going to be L square. Yeah, that's just like a square of length L. But then you have to assign the direction to it because now we already agreed that the vector of an area pointing perpendicular and pointing outward from an enclosed volume. So that means your area vector is supposed to point outward like this. Okay, oh, let me erase that arrow here so you won't get confused there. Okay, so there you go. Let me just, there you go. Let's make it worse, I guess. Here we go. All right. Okay, so the area vector is going to point in the negative x direction. You guys with me? So that means what I can do is I can say A vector is just L square. And then I say minus I hat. You guys agree with this notation here? Okay, so, I mean, but in reality, you don't need to write the whole thing, right? But for now, just saying that, just for clarity, that your area on the left, the left side surface has the direction pointing in the negative x direction. Cool. So now look at the front side. You know now you have to give the direction to this area to be pointing in the perpendicular direction to the surface, and it is in the positive x direction. So I can say the area on the right is L square I hat. You guys with me? So now let me call this the left and call that the right. And now I'm writing in a vector form. Isn't that cool? All right, so I hope by showing you this, now you start to understand how you assign a area vector into an actual surface. Okay, now come back to us. So what we want to calculate is the flux though. So what is the flux through the left side? So look at this electric field pointing in the positive x direction, right? So if you move toward this one, electric field is pointing to the positive x direction, but your area vector pointing toward the negative x direction. So it makes 180 degrees with each other. So what I can do is it's going to be E dot A on the left. Cool. And just this one alone is going to be the size of A times the size, the size of E times the size of A and cosine 180 degree. And that's what it is.
Okay.
Okay, now let's turn our attention to the blue, the right side surface. As you can see, the electric field vector at this point also pointing in the same direction. So that means the angle that it makes with the area vector A is 0. So what you get over here is going to be, okay, you always write E dot A on the right. There's no change. However, the angle between them is just 0. So it's going to be the size of E times the size of A on the right, and then cosine 0. All right, I forgot to put left here. Okay, cool. All right, then. Now I just substitute the number here. E L square. Cosine 90 is -1. For the blue, E L square, cosine 0 is 1, and that's it, guys. I get 0 at the end. You done.
Okay.
Got that one? Cool? รู้เรื่องไหม It's not too bad, I hope. All right, so if this is not bad, try the next one. All right, it's going to get harder and harder. Okay, keep going. Next. Okay, guys. So this is actually, it's already not bad for like the exam level questions. It's something around here already, so don't have to think too much. I'm not going to try to do anything super hard, but if you understand this one, I think you understand how to calculate flux through any surfaces. All right, so I think this is the good one, the good one. Consider a closed triangular box resting within a horizontal electric field having the magnitude given. Calculate the electric flux through, okay, now you have a vertical rectangular surface. Okay, so let me highlight green here. So that's your vertical rectangular surface over there. That's the green one. Cool. All right. And the slanted surface, so that would be, okay, let me highlight it blue there. Oh, no, that's not the one. Sorry. Okay, let me draw the black one first. Okay, so the slanted surface is the one that's slanted, of course. So that's the blue. So that's the one that makes some inclination there. There you go. There, that's a blue. Cool. And the part C, entire surface of the box. You want to give it a try, this one, guys? Yeah? All right, first, try the part A first, guys. I think it's like I'm going crazy, right? I'm just like talking to myself with the camera and all this stuff. And like it's been 2 years, so it's like my mind is just like going weird. I'm making friends with the PC camera right now. Okay, guys, part A. Vertical rectangular surface. What is the flux through this surface, guys? What do you think? All right, this is going to be the easy one because we just saw from the previous exercise. Okay, if you look at the green surface, just to be a little bit clearer, I'm going to highlight it green over here. So what is the direction of this area vector, guys, for this one? Of course, you need it to be perpendicular, right? You want it to be perpendicular to this and pointing outward from the enclosed volume. So that means your area vector of this surface is going to point, okay, let me write it big here. It's going to point backward there. Let me call this a vertical. There you go. Cool. Okay, just to make the whole thing sort of like smooth and all this stuff, what should be the slanted surface vector? What do you think? Of course, it's going to point perpendicular to it. So it's going to point, that's what we call A sub S vector. That's perpendicular to that. Cool? All right, just to make it a little clearer, I don't know, is this clear enough for you? Even look at the side view, guys. Side view. Side view could go something like this. Side view. Okay, the green is the vertical, the blue is the slanted, and the electric field vector is, okay, I don't know, am I writing nice enough for you guys? Electric field vector is pointing in this direction here. Cool. All right, so I'm trying to make it coincide with the upper figure over here. So what you have here is the area vector for the vertical one is going to point perpendicular to it. It's going to point backward here. The slanted surface vector will point perpendicular to it. It's going to go like this. Isn't that cool? All right, then. So let's start from the green, shall we? Okay, so look at the green, guys. The electric field vector at this point is pointing toward your right side. And the area vector, the vertical one, is pointing to the left. It's making 180 degrees with each other. Cool. Yeah, that's 180. So now part A, what you can say is the electric flux through the vertical surface. So let me put the subscript V in there. It's just going to be E dot with the A vertical vector. And that is going to be the size of E times the size of A vertical. And then times the cosine 180 degree. Isn't that cool?
Okay.
And now you guys know it's going to be negative. Why? Because the flux that is negative means the electric field is trying to enter the enclosed volume. It's trying to get in, right? So that's why it's negative, which is good. Perfect. So what you get over here is going to be negative E times the area of A vertical is just going to be the height times the width. So we can just multiply that. So it's going to be 0.1 times 0.3. And you are done.
Okay.
Cool? Negative flux. You can substitute electric field magnitude in there is 10 to the fourth. That's fine. So that's easy one. All right, guys, try again. Everyone, I want you to try part B. I want you to figure out the flux through the slanted surface. Oh, come on, man. Go ahead. All right, I really want you to do this. So what will happen on the slanted surface, guys? Well, Ajahn, that's not bad. So let me move this. I cannot move it. Okay, fine. Why? Cannot move this. Okay. Okay, that's okay. All right, so what we have over there is, of course, you're going to have to take a look at the electric field vector. It's going to point in that direction, yeah? The A sub S vector is point perpendicular to the slanted surface. Now you need a little bit of geometry over here to help. Now they already given you 60 degree on top. This is the apex angle on top right there. So this is going to give you 30. If that 30, this is going to be 30 as well. And so that come back to you to be 60 up here. Cool. So that means for the slanted surface, the area vector is making 60 degree angle with the electric field vector. So, Ajan, go ahead. Ajan, do it. Just kidding. All right. So E dot A sub S. It's going to be E magnitude, A sub S magnitude, and then Ajan just do the cosine 60. Okay? All right, guys, follow me closely here. What is the size of the A sub S? But then, of course, you want the size of A sub S is going to be the area here that I'm highlighting right now. The slanted surface area, correct? Okay, so if you want this size, so you know the length already over here, that's 30. So what you need is the hypotenuse, right? You want the length of this side over here. Let me call it X for now. So you want the X hypotenuse, which of course you can figure it out because you know you want the X over here. You know that adjacent to 60 degree, this is 10 centimeter. Okay. You guys with me? So can you figure out the X from trigonometry here? Well, that's no big deal. It's adjacent over hypotenuse 10 over X is cosine 60. You guys with me here? Okay, just let me know if I lost you somewhere. Okay, so when you look at the bottom triangle over here, so it's adjacent over hypotenuse there, give you cosine 60. So that means X is just 10 centimeter over cosine 60, yeah? All right, so I substitute that back in there. E times A sub S. A sub S is the width times the length. So it's going to be 30 centimeter times the X. So it's going to be 30 times X. And then cosine 60. But then we just figure out X is just 10 centimeter over cosine 60. And then you have cosine 60. That cosine 60 cancel. Do you see something here? Wow! You got my point here? You see my point here? Do you? At the end, the electric flux through the slanted surface is just E times 0.1 times 0.3. And that's it. Which, of course, eventually it's going to cancel with the value that you got from the vertical flux. And that you eventually going to get net zero flux on this. Why? Because you're not going to get anything from the front. The front surface give you zero flux. Okay, that's for sure. So I can just highlight this one. This give you zero flux. The back side over there will give you zero flux as well, because there's no penetration through the front and the back. And what about the bottom? Well, at the bottom also zero flux. See? So there's no flux to the bottom. There's no flux to the front. There's no flux through the back. There's only flux penetrating through these surfaces. It's just only from the vertical and the slanted, right? But then we already calculated vertical to be part A, the slanted to be part B, but they are just opposite each other. Because part A, flux is just trying to enter the volume to get the negative flux. And part B, whatever the flux that get into the vertical surface, it's eventually going to go out. It's exit on the right on the slanted surface. So in is equal to out. So the net flux in part C, you're going to get zero. That's for sure. But do you see my point here, guys? Do you see?
Okay.
I don't need to do trigonometry whatsoever. I don't have to do this. This I don't need. Why? Okay, guys, come back to this again. Remember what we discussed last time? Look at the blue one more time, guys. Look at the blue. This is the slanted surface, correct? Okay, that's gonna look a little ugly, but that's my point. I want you to focus on this. That's the blue. And you see that the electric field is in the horizontal direction, right? What we just did over there, we had the area vector. Okay, let me do this. Okay, I think you guys can sort of like get confused with my drawing now. So I'm going to get one more page here and I'm just going to draw it hugely just for you to see. Okay, one more time. Guys, follow closely. You have the vertical. You have the slanted, right? And you have this bottom here. The slanted surface has the area vector pointing perpendicularly, yes. Electric field is pointing in this direction, yes. But then when you really want to do the dot products, you want these two vectors that are pointing in the same direction to multiply. So what you did was just you do this, break this vector into components. There is an area vector that point in the same direction as the electric field. And there is an area vector that point perpendicular to it. So this is the A slanted. Okay, but now you already figured out that this is 60 degree. So this A is going to be A slanted cosine 60. This is A slanted sine 60. The sine 61 you don't care because this portion of the area is perpendicular to the electric field. You throw them away. So you only want the one that is parallel to the E, and that is the A sub S cosine 60 right here. And then you just multiply by the E, right? This is what you did. However, remember what we did. Each area vector must be associating with the real actual area, right? Which is going to be perpendicular to that vector. What would that area be for the AS cosine 60? Oh, yeah, Dan. We just calculated that it's the same as the green one. This is AS cosine 60. You guys with me here?
Okay.
And what is this? Think of it this way, guys. If the electric field is a light, so that means if I shine like a flashlight in this direction, in the direction of E, onto the slanted surface, the blue, and I have the screen here waiting for you. This is a screen. What should be the shadow of my slanted surface, the blue surface on the screen? Yeah, of course. My shadow is going to be exactly this height. You guys with me here? Yes? And that's what it is. This is A sub S cosine 60, guys. Woohoo!
Okay.
Is the, once again, we talked about this briefly, is the projection of the area taking the E to be the direction of the light that you're shining on that surface. And when it's casting a shadow, the size of the shadow is going to be the area that is perpendicular to that light. Yes? Does that make sense? All right. Yes? Any feedback here? All right, you guys still with me, right? Okay. So that's what it is. So when you look at this one more time, and if I were to look at this problem, I don't have to do that trigonometry like 10 centimeter over x equal to cosine 60. I don't have to find the hypotenuse over there because I can tell you right away that I just need to take the E and then multiply by the shadow of my slanted surface. And the shadow of that going to be the same size as the A vertical, same area as the green area there. Cool, done.
Okay.
All right, guys, you guys still confused, I think. All right, because you're still like, okay, Dan, I kind of get it a little bit. I know it's a little bit about projection. That is about like a shadow casting onto a screen perpendicular to the electric field or perpendicular to the light that you're shining on it. It's kind of getting an idea. I want to double check that you understand this. Try next one, guys. If you get this one, you're almost done. Guys, try this. Woo! All right, seriously, I want you to calculate this. All right, I'm not going to give you the solution just yet. I'll give you like 2 minutes to think about this one. You have a cone with base radius R and height H is located on horizontal table. The horizontal uniform field E penetrates the cone as shown from left to right. Determine the electric flux that entered the left-hand side of the cone. They just want the left-hand side of the cone because now we know the gag here that if they asking what is the net flux on this cone, you're going to get 0 again, right? Because whatever the electric field lines that enter this cone volume inside is going to come out. So when in is equal to out, the net flux is 0. So you guys sort of like familiar with this scenario already. But now they just only want the flux that enter just the left side of the cone. So that means they just cut this cone in half, pretty much. Just cut in half. And they just want the one that enter the cone. They just want the entering part of this flux. How much would that be, guys? All right, 2 minutes. Go ahead. There's supposed to be like a background music at this point. Yeah. All right, slowly, guys. Think about this one carefully. What should be the electric flux entering the left side of the cone? If we were to do the quiz, this is going to be the quiz that you have to submit your answer something. Yeah. All right, but we don't have that. So, but this is a good quiz question. Yeah. And I won't let you go until you figure out the answer. Still waiting. Anybody? Any participation? Yes? Hey, guys, you still with me, right? It's like I'm alone in this world right now. All right. Okay, but at least I can see your a participant's name over here. So it's kind of like feel all right. Kind of feel warms for you guys. Okay, how much, guys? What's the flux? It's not going to be difficult, right? When I lead you in like this far, it's going to be something simple, yeah? Okay, so if you really want to go like traditional way of finding flux, it's going to be E dot A, right? Now you're going to hit like a big wall here because look at this, Batan. It's kind of not easy because every time that you want to figure out the flux, let's say if I interested in like a tiny piece of the cone over here, the area vector will point perpendicular to it while the electric field is pointing in this way, right? E is here. The A is on the side. Oh, let me use the blue here. The A on the side, it goes something like this. And who will be able to figure out this angle? That would be crazy, right? And the time, what about the backside? That would be crazy. The A vector will point in crazy direction. So that's my whole point. You don't need to do that. And this is called projection that we just discussed. Think of the E as the ray of light. You're shining a flashlight in this direction here onto this cone. You have a screen on the back waiting for you. Okay, let me remove this part here. If you don't want to do that. Let's say even have a big screen on the right waiting for it. What do you think you're going to get a shape of a shadow on the screen? The screen is perpendicular to the light direction. Well, yeah, Dan, I'm going to get that triangle shape. You guys with me here? So that triangle shape will cast as a shadow on here. That's a shadow of the cone. Cool? And actually, that is the A perpendicular that we discussed since the beginning of the concepts of flux. Because you only care about the components of the side surface of the cone that actually perpendicular to the electric field. So you only care about the area that actually perpendicular to the field, which is just the shadow that casted on a screen that is perpendicular to the field. So what's the size of this one? Half times the base, which is 2r, times the height, which is h. 2 cancel is RH. So the net flux through the left side of the cone is just E times R times H, and you're done.
Okay.
Deleted it. Hope this is easy enough for you to see what we're doing over here. Yeah. That's it, guys. That's the concepts of the electric flux. And you will do exactly the same on the right, except, well, John, wait a second. You are looking at the left side of the cone. The area vector actually point to your left side. Yeah, you're right. So actually this area on the left is supposed to go left side. But electric field right now is pointing to the right. So you are making 180 degree with each other. So, Bajan, it's supposed to be negative. Yeah, that's what it is.
Okay.
Because the left side of the cone, you have electric field penetrating inward, trying to get into the enclosed volume. So that's why the flux is supposed to be negative. And now if you want, you can just say, if you want the flux going to the right side of the cone, it's going to be the same, but it's positive because the electric field is trying to exit the cone on the right side. And that will lead you to the net amount of flux through this cone supposed to be 0, just like before. And you're done. Yes or no? Okay, I hope it's not bad. All right, so if you kind of like get this feeling of how to calculate electric flux and kind of like get the feeling of what does it mean by the projection is exactly the same as doing the dot product, because the dot product is trying to make the product between two vectors that are pointing in the same direction. When you say same direction, you have two choices. It's either 0 degree or 180 degree, right? So that means you want the dot product. That means you want the product between two vectors that are parallel or anti-parallel. However, we defined the area vector to be the direction of the area that is perpendicular to the actual surface area. So when you have E perpendicular to the A vector, is the guarantee that is you are looking at the E that actually going through the surface area perpendicularly. That's the whole story about the flux calculation. Yeah. All right. So if this is pretty good, then this is now a good place. All right. Any questions before we move on? So this is like sort of like the peak of today's lecture now. All right. So this is a point where, okay, Dan, I got it. I know how to calculate the electric flux. I know how to calculate the flux through like a weird shape. I don't care. All right. So one more example. Okay, just one more time. So if think of it this way, if my face having electric field going through in front of my face, right? What is the net flux going through my face, guys? Of course, when you look at my face, it's going to be crazy, right? Because I will have the area vector point in crazy direction, right? But all you need to do is just looking behind me. I don't have it, but if I have a screen on my back and I cast the light through my face, you only have to look at my shadow. So the shadow of my head, that will be the surface area that you need to multiply by the electric field that's going through my face right now. Cool? That is going to be the same as the amount of flux going through my face. You don't have to do E dot A every surface is on my face. You just look at the total surface of my shadow and you multiply by the electric flux. Electric field, you get the flux, you're done. Cool?
Okay.
All right. So I think that's like an extreme example just to say in case of like you have like a super irregular surfaces and then what you want. All right. What I want is just the shape of your shadow. That's what it means. All right, guys. So if you guys sort of understand how to calculate flux, here we go, guys. This is it. Welcome to, it's supposed to be like a orchestrated, or I don't know, whatever. Gauss's law. The whole point that we're doing the flux calculation is this. Gauss said, where does the electric field lines comes from, guys? Of course, it comes from the charge. There must be some charges that generating the field. And that field, we visualize it through the electric field lines. And we just said electric field lines can be quantified by flux. So everywhere that you have evidence of having some flux, there must be the source of that flux. And that source must be the charge. You're done. That's
Okay.
Gauss's law. So Gauss said, for any imaginary, you can imagine your own surface, but as long as it's closed surface, which eventually we're going to call them Gaussian surface, right? To honor him, that who came up with this theory over here, this law over here that says any closed surface that you can imagine, the amount of flux through this surface will be exactly the same as the net charge inside. That's the key, inside. Divided by epsilon naught. Epsilon naught is too bad because we want to work within the SI system and we didn't introduce any constants back in the day that we define your flux. So that's why we have to put some constant here. So that's it. So the key is actually very simple. Flux tells you the charge. That's it. All right. Epsilon naught just here, just to make units, everything work perfectly within SI system. But the key is flux means charge. Flux means charge. Look at this, guys. It's going to be super simple. See? Let me ask you this. I have a charge Q sitting there. Let's say I have three surfaces, S1, S2, and S3. Which one has the largest amount of flux, guys? Which one? S1, S2, S3. Which one should have the largest amount of flux? Having the charge Q in there. And everyone can imagine that every charge will have electric field around all the time. We learned this like since the beginning of this electric flux module, electric field module here. So everyone knows there will be electric field lines coming out of this charge Q, right? So you saw that, oh, okay, then there is a radiating electric field coming out from this Q. So we have three surfaces, S1, S2, S3. Which one has the largest amount of flux through it? Without doing the real calculation here, just by looking at it. Which one, guys? S1, okay, there's somebody participating now. Okay, anybody else want to try? S1, S2, S3. The answer is they're all the same. Okay. Because flux is the electric field line. And you look at this one. If you count them, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. These 12 lines, even though in reality it's not 12, but what I'm saying here, based on this figure over here, those 12 lines penetrating through S1, S2, S3. Same. Why? Because it all came from this Q. You have fixed amount of lines. And once you wrap this charge with some weird surfaces, or it couldn't be, it doesn't have to be weird. It could be a sphere, it could be weird, doesn't matter. But because you wrap around this charge, you're going to get fixed amounts of electric flux. No change. You see what that's the Gauss's law it's trying to say? Any closed surface if you can calculate flux through that surface, it will give you the amount of charge inside. Don't tell anyone. This is sort of like, our little secret here. Yeah, look on the right. Now there's another surface here, but as you can see, this surface does not include the charge inside. So when the charge is coming from somewhere else outside, electric field must be, of course, generated from the charge Q, but it's going to have a point where the electric field is entering, but those entering field, eventually they're going to exit. So we already saw from so many examples in the past, whenever you have electric field coming from somewhere else, the net flux within this closed surface go to zero. See this? Electric field came from whoever, I don't know. But at least you can tell there shouldn't be any flux in this cone. I'm sorry, there shouldn't be any charge in this cone. Because that, if there was some charge in this cone, there must be some electric field leaking out. Right? Leaking out from this cone. But there's none. The net flux is zero. That means the net charge inside must be zero as well. Look at this. What do you think about this? Electric field came from somewhere else. I don't know what it is. The net flux from this is zero. What does it mean? It means within this wedge, there shouldn't be any charge inside. Otherwise, the net flux shouldn't be zero. Look at this. Electric field came from somewhere else. And the net flux in this cube is zero. So what does it mean? It means within this cube, there shouldn't be any non-negative, there shouldn't be any charge in it. The net charge in this box is supposed to be zero. Okay, guys, so you got it. So that's what I told you since the beginning, that once you understand how to calculate flux, Gauss's law is so simple because flux is just the evidence showing that there is charge in there. If no flux, no charge. When I say no charge, I mean neutral. It could be like positive equal to negative, right? But I mean, the net charge inside must be zero. So it depends on the text. The text say included. They use that INC there, included inside the enclosed volume. Some textbooks say inside, some textbooks say Q in, doesn't matter. But the point is, that is the clue. Okay, guys? And I'm just going to show you this before the break, just for you to be able to think about this one. One more time. The four figures show a cross section to Gaussian sphere. So it means Gaussian just saying that it's your imaginary surface. So you have two spheres and two cubes, okay, wrapping around this positive charge at the center. Rank the net flux through four Gaussian surfaces. Which one give you the greatest flux, guys? The A, the B, the C, or the D? Very good, very good. They're all the same. I can even tell you the flux through these all four is going to be Q over epsilon naught. I'm done.
Okay.
Is that too simple? Yeah. Seriously. Try again. Yeah. So this is conclusion, right? You can read this one through. You still don't even know what I'm talking about. So it's better to just skip this slide, and eventually I'm going to show you one thing. And eventually, all right, this is going to be before the break here. So look at this one. If I have a net charge Q and my Gaussian surface is just a sphere, even though because you have to imagine this surface yourself. However, the reason that I picked sphere because of the symmetry. All right, we'll talk about that after the break. But for now, let's say, okay, Ajahn, it's a dot, it's a point charge. So what kind of surface that allow you to do things very simply is just say, okay, I'm just going to pick a sphere having the charge at the center. Okay, so by having that, so your surface area will have the vector perpendicular to it in the radial direction. And because the electric field coming out from the charge is pointing outward, we already agree on it. So that means your electric field is also pointing in the radial directions as well. So what you can see right now is your area vector are parallel to the E electric field vector. So it's making a 0-degree angle with each other. So the net flux just by this tiny, tiny flux here, so let me call it the D flux here, is going to be E dot with the, okay, because this one goes so small, is going to 0. So it's going to be E dot with the dA. This is my neat flux through this little piece of area. But of course, you're going to have to keep doing this everywhere, everywhere. Keep doing this, keep doing this, keep doing this, keep doing this. But as you can see, no matter which area you're talking about on this surface of a sphere, the conditions stay exactly the same. With me? This is my dA vector. This is going to be my E vector because E and A are pointing in the radial direction. That's why we pick a sphere having the charge at the center. You can go the other side over here. Yeah, so the area vector is going to point perpendicular to it. There's no emergency here. That's fine. So what you have over here is electric field vector also point parallel to it. See? So, okay, no problem. So that means no matter where you are, this equation giving you the flux through any piece of area on this sphere. So what you need to do is just sum them all. Just sum them up. So you follow now. So the net flux through this sphere is going to be just E dot dA here. That's what you're seeing over here. That circle sign over here just is saying that this surface is okay. It's guaranteed to be closed surface. Now, the E and dA are parallel to each other. So it's going to be E dA cosine 0, which is just E dA. Cool. However, because at the same distance from the charge, I don't know Coulomb's law. I don't know. But I'm just saying that, just using a simple argument. Well, hey, it looks symmetric around this charge. As long as you stay away from the charge at the same distance, there shouldn't be any reason why I get stronger electric field, right? I'm just using just a symmetry argument. I'm just saying that, hey, by symmetry, okay, electric field should be exactly the same everywhere on this sphere because they all look the same to me. So I can pull E out from the integral. I have left with just the integral of dA. What is this? Of course, it's just the surface area of a sphere. So it's going to be 4 pi r squared. And now I'm just using the Gauss's law. Gauss's law say, whatever flux that you calculate here, which is simply just E times 4 pi r squared, is going to be equal to the charge inside. There you go. Simple. Q divided by epsilon naught. Do you see what I see here? I can move things around here and say E is 1 over 4 pi epsilon naught Q over r squared. And I am getting my Coulomb's law back from Gauss's law.
Okay.
All right, guys, this is the wow moment here, guys. You're supposed to be like, oh my God. Okay, or it's like, okay, this is like jaw-dropping second over here. So what you have over here is, this is Gauss's law. Gauss's law is now equivalent to Coulomb's law. You can use Gauss's law to figure out the electric field this way. All right, and your task is just come up with a good Gaussian surface that allow you to do the flux calculation easy enough. And once you have that relationship, then you can extract the information about the electric field out of it. And that's the way we are going to apply Gauss's law there. Cool? All right, guys, so we're going to take a break right here.
Okay.
And come back with more application after the break, yeah? What is it? Okay, so the key stuff that we're about to do here is, now you got the point, right? You need to come up with your own surface. Okay, that's one thing. And then hopefully that surface is supposed to be something that's allow you to do flux calculation easily enough. It won't give you any complexity in your life. We already had enough of that. All right, I don't want to get anything anymore. So we pick the surface depends on the symmetry of the problem. When I say the symmetry of the problem, think about this. Back in these problems over here, you might be wondering about time, why did you pick a sphere to be a Gaussian sphere? Why you pick a sphere to be the shape of the Gaussian sphere? The answer is simple. Imagine that in reality, if you have just a charge Q over here sitting in space, nothing else. Nothing else. All right, you have to imagine with me a little bit here, right? Okay, so nothing else. Can you tell which up, which down, which left, which right? No. You got that?
Okay.
There's no up, there's no down, there's no north, there's no south, there's no east, there's no west. Because you only just a point in space. So that's why when you look up, look down, they all look the same to you. When they all look the same in all directions, that's why this has a spherical symmetry. Does that make sense? Okay.
Okay.
That's what it is. So once again, so every time that you are talking about something that look like a sphere like this, so now you are given as a solid sphere of radius r. If this solid sphere of charge is sitting in space, it's like super black, like pitch black. There's nothing else in space. There's nothing. There's nothing for you to hold on to. There's no north, there's no south, there's nothing there. So when there's nothing there, the symmetry that we are talking about over here is going to be a spherical symmetry. Does that make sense? This is a reason why if you are dealing with a spherical shaped object with a charge on it, we are going to build just a sphere wrapping around it. And we're going to utilize the symmetry that we're talking about over here, right? This is going to be the shape of the Gaussian surface that we're going to build. I don't know why I write this one on top of the one already there. But that's what it is. Why do we want this? Because every time that you slice off a piece of area on this surface, the area vector will point in the perpendicular direction. Now you're sort of familiar with this, right? Because the area vector points perpendicular to the actual surface and pointing outward from the enclosed volume. Perfect. What about the electric field? Don't forget, we are not trying to use any Coulomb's law whatsoever. The only agreements that we have is just like we assume that electric field coming out from a positive charge and enter the negative charge. But once again, imagine that you are in a blank space. There must be electric field coming out of this. But when they say coming out of this, it's supposed to come out in all directions equally, right? There shouldn't have any direction that electric field is stronger than the other. So that's why you can assume that electric field supposed to be pointing outward equally the same in all directions. You got my argument here now? So this is a reason why we can say electric field is pointing in the radial direction with the same magnitude in all directions. And that allows you to do the flux calculation over here very easily. You can say flux here is going to be my mini flux here. It is going to be E vector dot with the A vector, which is just a dA vector. And because they are parallel to each other, it's going to be E dA cosine 0. And that is just E dA. Isn't that easy? Yeah? Okay.
Okay.
All right. So let's do it, guys. So you got an idea here. Okay. So let me erase that and just start from the beginning. Now you have an isolating solid sphere of radius capital R. Oh, it's supposed to be a mini r there. Sorry, guys. Okay. Small r. Oh, capital R. That's correct. Okay. That's of this sphere here. Okay. So it has a uniform charge density. Now here we go. Remember the density, but this density now is in 3D. So this is charge per volume now. We're not having like a rod or anything just like before. Now this is a real sphere. So that is the amount of charge per unit volume. So that means given the rho, you can figure out the net amount of charge in this ball over here. It's going to be just rho times the volume of this sphere. And the volume of a sphere is 4/3 pi r cubed. So that's it. So you can speak of the amount of charge inside this ball, either in terms of the rho or in terms of the total amount of charge. Doesn't matter. They're all the same. Cool. That's up to you. Cool.
Okay.
Now, what is the electric field outside this spherical ball of charge, guys? All right. So you want to figure out the electric field somewhere beyond the size of this ball outside, right? So let's say you are at distance r away from the center of the ball. You want to figure out the electric field here. So we just create our imaginary Gaussian surface. So that means we draw a Gaussian sphere having the radius r right here. Cool? All right. And then what you want to do next is, what is the flux on this surface, guys? Go ahead, do it. Okay. Give me a second here. So what is the next flux on this? It's simple, right? We already knew how to calculate flux on this one. It's a tiny flux there. So all you need is total amount of flux is the integral of this, which is just integral of E dot dA. Cool. So far so good. And because we already knew that E dot dA is just E dA cosine 0. And that would just be E dA. So what you have here is, it's just an integral of this. And it's just E can be pulled out with me. Yeah, because electric field magnitude is supposed to be the same everywhere. And you just have the dA to be integrated. And this one turns into E. Oh, it's already here. And that turned into this right there. Cool.
Okay.
Nice. All right. And just to be sort of like coincide with what we did, I'm supposed to put like a circle sign here just to say that, hey, the surface that we are looking at here is a closed surface. But at the end, you got the same results. It's E times 4 pi r squared. Why not? They look exactly the same as this one. No change. Electric field pointing in the radial direction, dA pointing in the radial direction. They all parallel, making 0 angle. So it's an E dA cosine 0. E can be pulled out. Integral of dA is 4 pi r squared. And then you always get the same amount of flux. Cool. Now, Gauss has said, this is the flux that you got. It's going to be equal to what? The charge enclosed. How much charge is being enclosed inside this Gaussian sphere, guys? Well, Ajahn, is the whole charge here. It's being included. That's where I put it here, guys. Capital Q. Take them all. That's the whole ball. That's the Gauss's law. It's simple as that. So I just take Q divided by epsilon naught. Now I can move things around. I just want to get to the E. So I move 4 pi r squared to the right side and I get this one and I'm done.
Okay.
How does it look here? Well, then it looks exactly the same as like KQ over R squared, which is cool. So it means as long as you have a charged ball and you are still away from it, you're outside this ball, right? You're not inside. The electric field around this ball, it looks like Coulomb's law, KQ over R squared, which is a nice result. However, now you have some sort of like a flexibility. If you don't want to talk about the net charge on this ball, you can speak in terms of the charge density if you like. So you can substitute Q with the rho multiplied by 4/3 part R cubed if you want. So that is another way that you can express your results under charge density. Okay, so you don't be afraid if you read the textbook or you read other books and then some books would like to talk about rho, that's fine. You can always convert between rho and the Q. It's just total amount of charge and the charge density, okay? All right, now, this might not be challenge enough for you. You want more? Now, next question. I want you to calculate the electric field inside the ball now. Whoa. Wow. Now, I don't want outside. Now, outside is easy. It looks exactly just like Coulomb's law. I want it inside. How would you do it, guys? Go ahead. Here we go. Do the same thing. Because the symmetry stays the same, no matter you are outside or inside, you still have the spherical symmetry. So you don't have to think in terms of what the shape of the Gaussian sphere you should pick. You still should pick a sphere anyway to be your Gaussian surface. However, the size of the sphere now is just smaller than the size of the charged ball. That's all. Cool?
Okay.
So now you create your imaginary Gaussian sphere to have a shape that actually is like a sphere, but it's a smaller. However, the arguments of everything, of the area, of the electric field, whatever, they should be exactly the same. What I'm saying over here is, if you look at the surface area, the dA, it's still pointing in the radial direction. What about the electric field? Electric field is supposed to be pointing in the same outward direction. Why? Because everything came from the spherical symmetry. Cool?
Okay.
Got it? I don't have any other arguments. I'm just saying that they all look the same in all directions, so everything's supposed to be in the radial direction. That's it. I don't have any Coulomb's law to use. I don't have anything to use. So what you have over here is, I'm just going to do exact same thing. What is the net charge on this Gaussian surface? You guys see this flux on this one is a mini flux. It's E dot dA, and it's just going to be EdA cosine 0, and it's going to be EdA again. See, you see this for the third time now. So the net flux is going to be integral closed surface of E dot dA, and it's just integral of EdA cosine 0. And it's just E integral of the dA for the whole surface. And now you get back to this. It's a E 4 pi r squared again. Okay.
Okay.
However, you want this to be equal to the charge and included inside this sphere and divided by epsilon naught, right? My question is, how much you're supposed to put in here? This is the clear usage of the Gauss's law. You only need the charge that is inside your Gaussian surface, right? And that is this much. You guys with me? Whatever go beyond this one, you don't have to take into account. It's not inside, it's outside. We already said when it's outside, the net electric flux from the outside charge will be 0 on any closed surface. So you don't have to worry about it. So all you have to worry about is just the charge in this mini, it's not mini, it's like a smaller, it's within the Gaussian sphere. That's what I'm saying. And this is where the rho is very convenient to be used. Because if you know the rho, which is the charge density, all you need to do is just multiply by the volume of this Gaussian sphere, correct? You guys with me?
Okay.
So with that, it means it just for third pi small r cubed. That's the charge. It's enclosed in there. So you just put the charge included inside this Gaussian sphere and plug it in there, and you are almost done. Okay, follow me here. So I just move 4 pi r squared to the right side. So 4 pi r squared epsilon naught is already in the front here. And you just take the q included to be 4 pi r cubed times rho over 3 came from here. Okay, so let me highlight that so you guys can follow. So this is the total amount of charge include here. That's there, and that's here. Cool. And that's it, guys. Just rearrange a little bit, whatever you like if you want. All right, so you can cancel this, cancel that. 4 pi can be canceled if you want. So you can write it as like a rho over 3 epsilon naught r if you want, and you are done.
Okay.
Isn't that cool? When I say isn't that cool, it means now you can see that the electric field inside the ball depends on R, which makes perfect sense. Why? Because when R is 0, you get 0 electric field. That means when you are standing at the center of the ball. When you're right at the center of the ball, everything's symmetric. So electric field vectors are supposed to be canceled themselves out. So you get 0 net electric field. But when you walk toward the rim of this ball of charge, electric field getting stronger, 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 but it's stronger in a linear fashion. Cool. So what it means, what I can say is over here. See? So if I sort of like draw the graph between the strength of the electric field with the radius of from the center of the ball, it will go something like this. This is the capital R, the size of the ball here. Inside the ball, electric field starts from 0 and it's getting stronger and stronger. Once you reach the rim of this ball over here, and then you go beyond this, it will go 1 over r squared down. Yeah, 1 over r squared come from here, right? Cool. So outside the ball, it looks like Coulomb's law. It's 1 over r squared. Inside the ball, it's r. And what's so good about this? Once you understand this, what do you get?
Okay.
You get the same explanation for the gravity. Remember? We discussed since the beginning of this module over here that electric field behave just like gravity. Yeah. So that means this explanation works for the gravity inside our Earth as well. So that means if you're at the center of the earth, which you probably cannot because it's like a super hot lava or whatever. But anyway, assuming that you can stand there, then there will be no gravitational pull. The gravity is going to be zero at the center of the earth. But then when you walk away from the center of the earth, the gravity is getting bigger and bigger, bigger. And then right at this, on the surface of this one, you get 9.8 meter per second square. And now when you get higher and higher, now your gravity will get smaller and smaller. When you go up in the mountain and stuff, the G is getting smaller and smaller, and it's 1 over r squared decreasing until you sort of like get out of this world. I mean, and then, you know, you don't have any sort of like the G getting super, super small on and on. Isn't that cool? All right. So, I mean, I find this one cool. But anyway, we didn't have the Gauss's law for the gravity. It's just, maybe it's just because the gravity is just so obvious that you always dealing with an object with the mass m. You don't have any, like, you know, distribution of mass and things that you want to go crazy and all this stuff. Even though it turns out that is, I mean, it's going to be the same Gauss's law for gravity. You can use it because it's the same concepts of field. But maybe because of the complexity of the electricity, you have positive charge, you have negative charge, and then charge can be distributed. So it's just harder for you to, you know, to deal with without the Gauss's law. But for the gravitational questions, you can get away with just, you know, Newton's gravitational attractions equation and all this stuff. Yeah. Cool. You find this helpful a little bit here. Hope you learned something today. All right, guys, try again. You're still having fun, I hope. All right, guys. So this is going to be, okay, don't want to make the material a little bit too strong there. So what I'm going to propose here is I'm going to make this one to be the last slide of the day. Sounds like a good plan? Yeah? Okay, because I think this is already heavy enough, but the point is I want you to have time to have this whole process here sort of like stuck in your head first before we move on to the next subject. But anyway, if you know how to do the flux calculation, and if you know how to do the Gauss's law, which is just a direct application of the flux calculation, yeah, this one's supposed to be easy for you now. Okay, guys, try this one. So this is our last exercise for Gauss's law, okay? You have a thin spherical shell, sphere again. Total charge Q distributed uniformly over its surface. Now find the electric field at point A outside and point B, and another point inside the shell. Okay, guys, this is good. This is a very good practice for you. I'm pretty sure. All right, so I'm gonna draw a shell right there. So this is, okay, let me draw like a huge one here. All right, so this is a shell. And we know that there is a total amount of charge on here to be Q distributed uniformly across. So let's start from the outside first, shall we? Okay, because we already knew that it seems to be easy enough for you to do. Once again, is a spherical shell. It has a form of a sphere. So your Gauss's law is supposed to look like a sphere again. Does that make sense?
Okay.
By symmetry. Think of it like you have a shell sitting in space. No, they all look the same everywhere. So that's what you're going to do. You're just going to draw, imagine your own Gaussian surface wrapping around. Cool. Yeah. And the nice thing about this one, once again, the area vector is pointing, let me draw on the side here. Area vector is pointing outward here. Electric field vector by symmetry is supposed to go in the radial direction as well. Nothing else. So now you start to feel comfortable doing this. What is the net flux on this surface here? So let me call this outside. So it's going to be the integral of E dot dA from Gauss's law, right? So let's work on this one first. So once again, E and dA are parallel. So it's going to be E dA cosine 0. And once again, cosine 0 is 1. It's supposed to be the same everywhere because by symmetry, they shouldn't have any direction has a stronger electric field than other directions. The integral of the dA is just 4 pi r squared. So let's assume that your distance right now is small r. So let me put r squared there. That's the surface of the sphere. Done. That's the left side of the Gauss's law. Gauss said this is going to be equal to the charge enclosed divided by epsilon naught. How much should I put in there, guys? Okay. How much is that? Well, of course, this Gaussian sphere wrapping the whole charge of this shell. So you should put the whole Q in there. You see how easy it is to apply Gauss's law? That's how simple it is. So that's it, guys. So what you can get from here is you just move 4 pi r squared to the right side. And you are done.
Okay.
This is the electric field outside. And it looks like Coulomb's law again. Yeah? Wow. So now you get a conclusion now. No matter you have a dot of charge, a ball of charge, a shell of charge, as long as you are staying away from it, the electric field will have the same expression, kq over r squared. That's the coolest thing, because everything came from the symmetry of the whole charge distribution. So what I can conclude over here is, as long as you have a spherical charge distribution, when you're staying away from it, it will look like Coulomb law no matter what. Cool?
Okay.
All right, now that's business is done. What about inside the shell, guys? Whoa. So, all right. So let me draw. Of course, by symmetry, you're supposed to pick Gaussian surface to be a spherical surface again. But now the size is just smaller than the radius of the shell. Cool? However, by picking this, everything looks exactly the same again. dA is still pointing out. Your E by symmetry is still pointing out. So everything looks exactly the same. So I think this is going to be the 5th time you're doing this. So for the inside, you're doing flux inside. It's just going to be integral of E dot dA. This is just Coulomb's law. I haven't done anything. Okay, but then E dot dA is, once again, it's just E dA cosine 0. I can draw this one. And E is constant, cosine 0 is 1, so it's the integral of dA again. And then you say it's just E4 pi r squared. Again, this is the 5th time you're saying this today.
Okay.
All right. So you have done this 5 times already. Okay. So that's done for the flux across this Gaussian surface, right? You have to equate this with the charge enclosed divided by epsilon naught. How much charge should you put here, guys? How much charge enclosed inside this smaller sphere inside? What do you think? Maybe too loud, yeah? How much charge inside this Gaussian sphere we are discussing right now? Whatever you're thinking is correct. How much? You guys still here? Q, okay? Okay, anybody else? Whatever you're thinking is correct. Maybe. Answer is nothing. Because the charge is on the shell. You guys with me? Okay, if this is positive charge. So let me say all those charge are just sort of like distributed across this shell, right? So when you imagine your Gaussian surface to be smaller than this shell, so this Gaussian surface does not include anything. See, there's nothing in here. There's nothing inside. So that's why you just say 0. So what I can tell you right now is the electric field inside is 0 as well. and you are done.
Okay.
Cool. And this one is actually very nice. So this one look just like, all right, even though it's not perfectly exactly the same scenario, but this is what it is as like a, it's called, maybe it's like a Faraday cage or something. So what it's saying is, if you are inside a container that has a charge distributed around and you are inside, there will be no electric field there. So you are safe. So it means you get a lightning strike and you are sitting in your car. Your car is made of metal. So that means when the car gets charged, you're supposed to be safe inside your car, even though you get lightning strike. As long as you don't have any part of your body touching your car's body. Yeah. So you should be safe. Yeah, of course. But in reality, it's not exactly that, because what we are studying right now is electrostatic. But the lightning strike is like, you still have charge going around all this stuff. So there are a lot of problems there. It's sort of like discharge the air around all this stuff. You have a lot of things going on. However, in theory, if you have a cage that is being charged and you are inside, you're supposed to get zero electric field. And this is part of the reason. I mean, this just give you connections, right? Even though it's not exactly the same again, but give you another connections. When you have your phone and you get into elevator, your phone signal dropped dramatically. Think of it that way. So at least it seems like electric field cannot survive something like a cage of charge. So you can assume that your elevator is made out of like iron or something like that, and they're supposed to have leftover charge and all this stuff. So you can imagine that there shouldn't be any electric field in there, all right? Even though, well, the story are different because your phone using electromagnetic waves to communicate with the radio stuff, so it actually cannot penetrate the wall. But at least it gives you the connections that if that wall is being charged as well, you shouldn't get any electric field inside your elevator anyway, something like that, okay? But in reality, you get something, right? Because your elevator might not be charged and the electromagnetic wave strength is pretty strong, so it can penetrate the wall of your elevator pretty well, on and on. All right, but if you go up, if you doing like watching the movies, and then they some criminals talking, they have some negotiation between criminals.
Okay.
And then when you meet, they have to collect your cell phones and put it in the microwave, something like that, right? So they hope that the cage of the microwave can protect the electromagnetic waves to get in, so you won't be able to communicate, something like that. All right. But anyway, I'm just going to give you some examples just for you to be able to remember this situation over here. That whenever you are being wrapped around with a charged container, inside the container have zero electric field. That's what it is. Okay, cool. All right. See, I hope we have done this 5 times inside within the setup of spherical symmetry, and we have all used Gaussian sphere to be your Gaussian surface, and we just do the flux calculation on this surface. And once we do that, just equate that to the charge inside divided by epsilon naught. That's the application of the Gauss's law. Cool. All right, guys. So that's concluded the stuff that we are going to do. I mean, I love to do today. Next time, all right, there is a big application of this, and we're going to look at another type of device in electricity or in electric circuits or that stuff that's called capacitor. So we'll have something that we can extend our understanding about potential, electric field, Gauss's law, and then we are going to talk about the property of capacitor. All right, it's going to be fun. All right, guys. So I think that's enough for today. Any questions? I think no. All right, guys, take care, stay safe, and I'll see you guys on Monday. Yeah. Okay. Bye-bye.